In this segment, I want to provide some examples, some image examples to illustrate the type of images that CT can provide. This is the image of a human head. We have bright, we have high electron density, so this is bone, high absorption. We can see the skull here, we see the sinuses here. The air is dark, these are the sinuses, that's the stuff that clogs up when you have a cold. We're looking here at an image of the abdomen. Now here's the spinal cord, is the spine, so we're seeing again calcification, high absorption. And we have obviously different intensities of tissue that give us intermediate results. They are not so easily discernible here. We have again lungs and the air outside, very low intensity. Now I mentioned earlier that the Hounsfield unit allows us to quantify the pixel intensity. So we can actually, in the operator, can set the pixel intensity on the computer display to depict different contrasts. So here are just the same image, taken the same image here, displayed in different ways. Here is one way. We don't really see much. It's relatively grayish. And here is a different highlight, and we're seeing very nicely, we're seeing the rib cage here, we're seeing the spine back here. And if we want to see soft tissue contrast, we can extend the contrast to see the very low intensities here, and we're starting to see the low contrast here in the lungs, but obviously the stuff that has very high absorption on the outside is now very bright. So we can play with the lookup table of image representation. Now there's a very famous example here from the Alps, from our mountains, not in Switzerland I must say. It's been in the end it's the Austrian-Italian Alps, at the Austrian-Italian border. This gentleman was discovered following the retreat of the glaciers. He lived some 4,000 years ago, and the question was, how did he die? That was the curiosity. It's a mummified body. We do not want to go in with a scalpel and cut him open. And his name is Ötzi. So here he is, wrapped up nicely in a blanket, entering a CT scanner, and that's what people have done. And what was found is that there was an arrowhead that was dislodged in his shoulder around here. So probably he died of the consequences of being shot by an arrow up there in the mountains 4,000 years ago. So this is a way where modern biomedical imaging was used to understand what happened to this person 5,000 years ago, showing this dislodged arrowhead. Now I want to go on with some examples from mouse imaging. This is the rodent spine, so it's a 3D image, CT scan of the spine. There is human mesenchymal stem cell treatment, and there is, at the site of treatment, there's significant bone formation here and here in these parts of the image. Here's an example from the head of an animal. This is pre-contrast agent injection. There's not much that we can see here. And after the contrast agent has been injected, we start to see some intensity here at this part of the vasculature. Same approach, we can take the contrast agents and, for example, image the vasculature of a placenta of a mouse. Now imagine how small a mouse is. Imagine how small a placenta is. We've got many mouse embryos in a mouse mother, and this is the vasculature of the placenta of a mouse with 13 micron spatial resolution. And finally, here an example of the mouse femur bone with growth hormone treatment, looking at the bone here, and then if you look at the structure inside, we see the difference in structure here, how this is affected by the treatment. We can very clearly see this very nicely with high resolution CT, micro CT. So now I want to do a brief summary of the CT. Computed tomography is done by X-ray absorption. That's the main contrast mechanism, and the main contrast that one can see is bone versus soft tissue or air. And this is the underlying reason for that is that one primarily measures the electron density rho. One can use contrast agents which increase the effective Z to depict vascular architecture or lesions. So contrast agents are useful. They can be used in addition. Here's an example of genetic research. We have insects. This is an insect with iodine contrast agent. We have beautiful contrast in these images here of this insect perfused with an iodine-bearing contrast agent. Now, some considerations on signal-to-noise ratio and contrast-to-noise ratio. In principle, we can just increase the cathode current until we saturate the filament, so we can increase this intensity, and so we can increase the SNR to almost unlimited levels, and therefore we can have a very high spatial resolution. That's what we see here with this very high spatial resolution image of the insect. However, in humans we are limited by the radiation dose that we can apply this to. Here's another example. This is a fish larva, just to mention how small the fish larvae are. These are the eyes of this fish, and again the very high resolution images. We see the brain here, spinal cord here, very high resolution possible in animals where we are not less concerned with radiation exposure. So to summarize, I've given you the basic principle of CT image reconstruction, some real-life considerations, and actually if we look over the decades, this is now this is over 4 decades of scanner development, we have seen quite a number of generations of scanners develop. We've had parallel first generation, second and third generation of the scanners, and this is what we are seeing here in the video are the different generation scanners. We're starting out with the simplest one. There was one scanner, one line collected at a time. Then we had a small fan beam, third generation, multiple scanners, etc. So in complexity, and actually in the meantime we're up to the 5th generation scanners, which are produced. We start with the 3rd generation, multiple detectors. Then we have the 4th generation. We have a detector ring, a large fan beam, and nowadays the scanning is done as the subject continuously moves through the scanner. This gives a spiral way of scanning the subject, very efficient. You can scan an entire body within a few seconds and then reconstruct it. Obviously now possible with today's computing power. As to the cost of a CT scanner, it is on the order of, depends of course on the country, depends on the currency here, but of the techniques we're discussing in this course, it is the cheapest technique aside from ultrasound. It's a few $100,000. Take it euro, dollar or Swiss franc, it's roughly the same thing. It's on the order of 100,000 to 200,000 Swiss franc.